Think about the largest financial vault in human history. It holds over $1 trillion in digital wealth. But if you went looking for the security detail, you'd find no laser grids, no attack dogs, no alarms, and not a single armed guard. All of that capital sits right out in the open on the internet, completely exposed to the most elite hackers on the planet. Yet it remains safe, totally untouched. The reason it survives is because the entire system is guarded by a single, invisible lock, a lock built entirely out of pure mathematics. To see exactly how this invisible vault functions today, we have to look back to the 17th century, at a specific problem in geometry. Back then, mathematicians were trying to answer a seemingly innocent question. How do you calculate the exact perimeter of an ellipse? A circle is easy because the radius is constant, but an ellipse stretches and squishes. Its radius constantly changes, which meant every standard algebraic formula of the era failed to measure it accurately. To solve the perimeter problem, scientists developed a new type of calculus called elliptic integrals. Over the next 2 centuries, those formulas were refined until they transformed into an independent mathematical object, the elliptic curve. This smooth, undulating line represents that evolution. The geometry of this curve provides the specific coordinates used to build modern digital security. This diagram shows a unique property of the curve that we can think of as cosmic billiards. If you draw a straight line through any 2 points on this curve, let's call them A and B, that line is mathematically guaranteed to hit the curve at a perfect third point. Take that third point, drop it vertically to reflect it on the opposite side of the curve, and you land on a brand new, mathematically locked coordinate. You can repeat this process indefinitely, and the geometry remains consistent. For hundreds of years, this trick was just a playground for math enthusiasts. But in 1985, cryptographers realized this predictable billiards game could function as a digital padlock. But there was a major engineering hurdle. To render a perfectly smooth curve, you need real numbers with infinite decimal places. When early computers tried to process that level of continuous detail, their memory would overload and the system would fail. To stop the machines from crashing and make this lock function in reality, cryptographers had to intentionally destroy the smooth curve. They achieved this by trapping the curve inside a finite field. This is a strict mathematical arena governed by prime numbers, where fractions are banned and only whole numbers are allowed to exist. This diagram visualizes what happens when you apply that rigid rule to our curve. It breaks apart into thousands of disconnected, scattered dots. It looks like a chaotic galaxy of stardust. But amazingly, the exact same rules of cosmic billiards still apply. If you draw a connecting line between any 2 dots in this field, you still hit a predictable third dot. The algebra survives. Out of all the possible curves cryptographers could have used, they selected one specific pristine equation, named Sec P 256K1, to serve as Bitcoin's bodyguard. It was chosen because its math is clean, with no mysterious parameters that might hide a backdoor. The arena for this specific curve is staggeringly huge. The prime number governing it creates a grid with 10 to the 77th power possible coordinates. That matches the number of individual atoms in the entire observable universe. When dealing with a grid that massive, isolating a single point without having the exact map is statistically impossible. Within this massive universe of numbers, every user starts at the exact same public coordinate. We call it the generator point. Your private key is essentially a set of instructions. It is the secret, massive number of times your computer jumps around that stardust galaxy, starting from the generator point. After completing all of those calculations in a fraction of a second, the final landing spot is your public key. That specific coordinate is visible to the entire network. So if a hacker knows your starting point, and they can see your final landing spot, why can't they just track the jumps backward to figure out your private key? The answer lies in what mathematicians call the discrete logarithm problem. Think about making a smoothie. You take solid, fresh fruit, throw it in a blender, turn it on, and you get a liquid. Moving forward is simple, but because finite field math eliminates the concept of division, calculating your steps backward cannot be done. It is exactly like running the machine in reverse and expecting the liquid to reassemble itself into a perfect strawberry. This one-way mathematical trapdoor is the barrier that secures the vault. Even with perfect security, there's a practical problem. A raw public key is a 256-bit string of alphanumeric code. It's incredibly long and practically guarantees you would mistype it during a transaction. This diagram shows the final transformation. To make the code usable, the raw coordinates are pushed through layers of hashing, like SA256, and bundled with built-in error detection codes. What comes out the other side is a short, clean string of characters. This is the standard Bitcoin wallet address that people interact with on their phones today. Those simple characters sitting on a screen hide a colossal, ancient iceberg of cryptographic mathematics right beneath them. This trillion-dollar system doesn't rely on central banks or physical guards. It is protected by the absolute, unyielding laws of mathematics.